Hello everyone, my name is Zhengyang Lu, and I'm going to introduce our recent work, Efficient Block Algorithm for Parallel Sparse Triangle Solve. All of authors are from China University of Petroleum, Beijing. This is the outline of my presentation. I would introduce from the following 6 parts. Now, I would introduce background of our work. The sparse triangle solve (SPTRSV) is a solution operation of linear equation Lx equal b or Ux equal b, where L or U is an upper triangle matrix or lower triangle matrix, b is a dense right-hand vector, and x is a result vector to be solved. There is an example. As we can see, there is a lower triangle matrix on the left, and x is a result vector, and b is a dense vector. Firstly, we can get the first element of x vector with the first row of L matrix, and the right-hand side is a calculation process. Then we can get x1 with the second row. We can get the x2 with the third row. Finally, we can get the last element with the last row. Finally, we can get the entire x vector by the serial sparse triangle solve. The level set algorithm is a typical method for exploiting possible parallelism in the input matrix. This method sees a matrix as a graph and divides its component into multiple sets. The components in each set do not depend on each other, so they can be solved in parallel. There is an example. The input matrix L of 16 no zeros can generate a graph of 4 level sets. Due to the dependencies, the component in a level must wait for the calculation of other components in its upper levels. For example, x1, x3 can be solved in parallel after x0, x2 are completed, and the components can be calculated in parallel in the same level. We have 3 motivations. First, we aim to make the data located better through dividing the matrix in the triangle matrix. We in this work explored 2D block layouts to naturally cut those long rows and columns into shorter segments. We in this paper will find the best formulation from various blocking methods and their parameters, and accelerate SPTRSV on modern GPUs. We first implement 3-block algorithm in our work. Now, I would introduce the block algorithms. This is a column block algorithm. A matrix can be divided into a number of column blocks, and each one consists of a triangle submatrix on top and a rectangle submatrix on bottom. The figure shows an example matrix of 4 column blocks. Row block algorithm similar to the column block algorithm. The row block algorithm cuts a matrix horizontally. Now each row block includes a rectangle submatrix on the left and a triangle submatrix on the right. For each row block, the rectangle part is firstly consumed by an SPMV, then an SPTRSV is assumed for the triangle part. The figure gives an example of 4 row blocks. Recursive block algorithm, unlike the former column and row block methods, recursive block approach divides a triangle matrix into two small triangle and one square or near square blocks, and the two triangle submatrix could be further recursively divided into the three parts. So the three-block algorithm executes the same number of SPTSV and SPMV kernels and possesses the same number of non-zero entries. The performance of them can be different. The bold blue and red lines means reading X and updating B respectively. Table 1 and Table 2 quantify the difference on updating B and reading X respectively. It's clear to see that the column block methods have disadvantage on updating B, and the row block method spend longer time on loading X. But fortunately, the recursive block algorithm achieves a good trade-off between the column and row block methods. Then we evaluate the three-block algorithm by running two representative sparse matrices on an NVIDIA Titan RTX GPU and plot their execution time on SPMV in the following figure. As can be seen, the SPMV kernels in recursive block algorithm almost always take less overheads than column and row block methods. As a result, we in this work will focus on further accelerating the recursive block data structure and algorithm. As we can see, there are three fingers. Finger A plot original input matrix L. It is reordered according to its level set order and turned into finger B. Then its two triangle parts are further reordered according to their level set orders, and the resulting matrix is the one shown in figure 3. It can be seen that the number of non-zeros is the square part of finger B is 11, which is higher than 8, the number of non-zeros in same area of figure A. Obviously, so the reorder, more non-zeros are concentrated in square parts to achieve better parallel performance. After reorder the sparse triangle matrix, the next step is to store it into a series of arrows. We assume the input matrix in the CSC format, including column pointer, row index, and value arrows as shown in following three arrows. Once it is reordered and saved as three submatrices, the triangle parts can be still saved in CSC, but the square parts should be transposed into CSR for using faster SPMV kernel. The blue item in the three arrows in following figure stores the CSR data of square part between the two CSC submatrices. When the matrix is further blocked into 7 submatrices, the two CSC submatrices are further stored with the same layout in the following figure. Two new squares are in light green and paper, and the triangle parts are in orange and light yellow. In addition, the squares blocks may be very sparse, meaning that a large portion of rows and probably empty. In such case, we store the CSR data with a simplified row pointer with an extra arrow saving the actual index We call this full mode DCSR in this paper. After the input matrix is divided and stored, the next step is to compute the small triangle and square blocks with SP, TRSV, and SPMV kernels. There are basically 4 kinds of structure in the small triangle matrix and 4 corresponding kernels. And for SP-TRSV kernel selection, we introduce 2 critical parameters to decide which kernel should be called for a given sub-matrix. Figure A plot the best SP-TRSV kernels selected. We can find the selecting principle of SP-TRSV kernel from the figure A. There are 2 kinds of structure in the square matrix and 2 corresponding kernel. And for SPMV kernel selection, we also use 2 parameters. We found that the selecting presence of SPMV kernel from figure B. Principle of SPMV kernel from figure B. The algorithm gives a decision tree for selecting the best kernel in the improved recursive block algorithm. The platform and the dataset are we used in the experiment. As we can see, this figure shows that the performance of the 3SP-TRSV method and the speedups of our block algorithm over the Sparse and the sig-free methods. On Titan X, the best speedups over Sparse and sig-free are 113.84x and 57.97x, and the average speedups are 5x and 10.34x respectively. On Titan RTX, the best speedups over Sparse and sig-free are 72.03x and 61.08x, and the average speedups are 4.72x and 9.95x respectively. To make the experiments more complete, we conduct a performance comparison of single and double precision of the 3 methods shown in the figure. As we can see, on the 2 GPUs, the ratio of double and single precision performance of the sig-free is around 0.9, and the ratio of our block algorithm is between 0.8 and 0.9, while that of Sparse is between 0.7 and 0.8. This indicates that compared to sig-free, our algorithm is a bit more sensitive on the cost for reading or writing floating point values, but compared to Sparse, our approach is relatively more insensitive to the floating point procession used. And this table shows the pre-processing cost, a single SP-TRSV cost, and the overall cost for 100, 500, and 1000 iteration of a complete procedure by using Sparse, sig-free, and our recursive block algorithm in double precision on the NVIDIA Titan RTX GPU. As we can see, our methods use a bit longer pre-processing time, but the overall cost for complete computation with a number of iterations is still obviously lower than Sparse and sig-free because of the much faster SP-TRSV computation. and we posted the source code in this link. This is our conclusion of our work. 1. We have implemented 3-block algorithm for parallel SPTSV on modern GPUs. 2. We propose an adaptive approach that automatically selects the best kernels and parameter for computing submetric divided. 3. Our experiments conducted on 159 metrics and on 2 high-end NVIDIA GPUs have shown an average 4.72x up to 72.03x and 9.95x up to 61.08x speedups over Sparse and Sparse method respectively. Thank you for listening. And if you have any question, you can contact us with this email address. Thank you.